Our fifth section of calculus is entitled Inverse Functions and Logarithms. In order for a function to be an inverse or have an inverse, we have to first meet the criteria of the function that we're trying to find the inverse of to be a one-to-one function, meaning that it never takes on the same value twice. All right, so writing this with function notation, I'm making sure that f of x1 and f of x2 are never going to be equal when x1 is not equal to x2. That's kind of confusing. So let's look at some just a Venn diagram of this. So suppose I have 4 elements in here, 1, 2, 3, 4, and they are mapping to, 4 elements in here, 2, 4, 8, and 10. No idea why I skipped 6 right there, but it happens. Now, a one-to-one function is going to make sure that the 1 maps to exactly 1 element over here, and that the 2 maps to 1 element over here, the 3 maps to 1 element, and the 4 maps to 1 element. This would be 1 to 1. The fact that each element only maps to 1. Now, while it's still a function, suppose I still have the 1, 2, 3, 4, and I'll just use the same thing I used over here, 2, 4, 8, and 10. Now, it's still okay. It's still a function if the 1 maps to the 2. Where'd the 2 go? The 2 went to the 8. We're still in line to be a function right here, but it's not going to be a one-to-one function as soon as the 3 goes to the 8 as well. So yes, it is a function. We're good because the 3 did not go to the 8 and the 3 did not go to the 10. That's perfectly fine. So each element over here on the left is mapping to 1 element on the right, but the fact that this 8 is being shared right here, it is not one-to-one. Okay, so that would be a little bit of a difference right there. Now we're going to be looking at this graphically, and so it's actually pretty easy to tell whether or not the graph is going to be a one-to-one function because it's going to follow something called the horizontal line test. A little bit different than my vertical line test. This time I'm going to draw a horizontal line anywhere on the graph, and the rule is that it cannot intersect the graph more than once. So let's see this in work. By the way, the bell's going to catch me here in a minute. It's going to be kind of loud, and I probably won't edit it out because I'll probably be right in the middle of something and I'll end up messing it up if I do edit it out. Okay, so let's look at my x cubed function. This is my good old snake on a plane right here. And I know it's going to be one-to-one because I can draw a horizontal line anywhere. And it only intersects it in at most one spot. So is this one-to-one? Yes. Every single x value has a different y value. And none of my y values are being shared by the same x value. You guys try this one. Let's see if it's one-to-one. Go ahead and draw it. Show your work on it as much as you can, and then see what you get. There's that bell. No, this doesn't work. It doesn't work at all. Let me show you using that function notation why. Is because this value right here at -2 looks like it's mapping up to, I don't know, well, I guess I could have drawn it a little bit more specific. Let me draw it a little more specific. Boom, boom, boom. -2 to the 4, plus 2 to the 4. There we go. So as you can see, like this function value right here at 2 is equal to 4, and the function value right here at -2 is equal to 4. While that's okay, it's still a function. It passes the vertical line test. It makes it so when I have 2 and -2 over here in this bubble, and I have 4 over here, they're both mapping to it. That's why it's a no-go. Okay? Or you can just say fails the vertical line or horizontal line test. That would be another good reason. But that's why it is using that function notation. Now, something else happens when you're dealing with inverse functions to the domain and range. So suppose that you have a regular function f with domain A and range B. Then what happens is the inverse function, the whole idea with an inverse function is that we're switching all of our x's and all of our y's. So that means that now what was my range, B, is going to be my domain. And what was my domain, A, is now going to be my range. All right? And I'm going to be able to define this by saying that if I had y equals f of x, that's going to be true if and only if x is equal to f inverse of y. So as you can see, my x and y swap places, and to show that they swap places, we throw this little inverse right there. Okay, let's talk about that little inverse right there. This is not, okay, this is not going to be 1 over f of y. All right, no, don't be that guy. This is just simply a notation trick that these math guys are using in order to show that we're doing the inverse. Okay, so we're not actually raising f to the negative first power. It's just a notation thing. So, they've told me some function values. It wants me to find the inverse. I'm going to overteach this by a lot real quick. Okay, so bear with me on this. I'm going to go back to my Venn diagram. And so these are all my input values that are in parentheses. The 1, the 3, what else do we have? The 8, that's it. And we see that the 1 is mapping to the 5. The 3 is mapping to a 7. The 8, it's coming over here to a negative 10. And so whenever we're going from left to right like this, and in the Venn diagram, we're saying that it's going through a machine, and that it's whatever f is mapping these numbers. Well, my inverse is going to be whatever brings this number back over. And so what's happening is, while this was my domain a while ago, and this was my range, whenever I'm starting to work the inverse, this range now is going to be my domain, and what was my domain is going to be my range. So I'm just looking at it backwards when I'm doing this inverse. So whenever it asks me for f inverse of 5, I'm just seeing that the 5 is making its way back to the 1. When it's asking me f inverse, I guess I went out of order, I apologize, 7 right there, the 7 is mapping back to the 3. F inverse of negative 10, I see the negative 10 is mapping back to the 8. Probably looking at this saying, well, I got a much better way of working this. Why don't I just switch these two numbers? Great. You're still just switching the x's and y's. I'm switching my domain and ranges. Either way you want to think of it, I'm interested in getting to this answer. But if you can kind of have this going on in your head with the idea of this Venn diagram, that would be awesome. So what this is going to allow me to do is have some cancellation equations. So what happens is, if I'm actually taking f inverse of a function, if I'm taking the inverse of a function and doing this composition, it should equal x every time, as long as x is in the domain of A. Okay. And even if I'm working this the other way, where I'm taking f of f inverse of x, that should equal x as well. And again, the reason this is working is because that we're just switching our domain and range. Okay. So how do we find the inverse? Well, we're going to find the inverse using this three-step process. So this three-step process, the first step is going to be, first off, I'm going to write y equals f of x. So I'm pretty much going to take the f of x out of my equation and work with y. I find that I'm able to work with y a lot easier whenever I'm doing the algebra on these steps. Okay. Once I do that, really you can do step 3 or step 2 next. You might see me do step 3 more. What I'm going to do is I'm going to interchange my x and y, and then that will have me actually solve the equation for y again. All right. If not, if I don't switch my x and y, what this says I need to do is solve the equation for x. Whichever way, if you switch your x and y, you're solving for the variable that's not solved for. So it really won't matter which way you work that. Those two steps are interchangeable. But I want you to do this at the very end. I want you to take the y back out of the equation after you exchange your variables and resolved, and I want you to rewrite it as f inverse of x to show me that that is your final answer. So let's find the inverse of this one, and I'm going to let you try one. So first step, I'm going to take out the f of x. I'm putting y in its place. Like I said, from here, according to your book, it says now just solve for x. I don't think I've taught it that way in Algebra 2, Algebra 2 or pre-calculus, I guess, for that matter. I went ahead now and exchanged my variables. You can wait and do that. As long as you do it at some point in this process, it's fine. But now what I'm going to do is I'm going to resolve this equation for y. So if I add 2 to both sides, and I take the cube root, I get my equation for y. Finally, let's just take out this y and change it back to an f inverse to show that this is the inverse of the equation. The reason I do that is because my y is actually equal to this up here. And it's not mathematically correct to tell me that y is equal to what this top guy is and what my final answer is. So it is a new function that I'm finding. And so I want to write it with my new function notation. All right, you hit pause. I want you to go ahead and just find the inverse of this function, and then we'll come back and we'll graph it together. This is what I have so far. Right? I want to talk about how to make this answer just a little bit better. Okay, so let's look at the graphs of these. I'm going to graph f first. I'll be using red for f. So I got my Schwoodt function. It normally went like this. And then a little bit of math I need to do on this first. I need to pull out that negative so I make sure I'm not doing a negative twice on there. And so I'm going to go ahead and then reflect this and then move it to the right one. So I should end up right here with the graph of my original function. Now, the way that this graph is going to correspond to its inverse, if you remember, is that it is going to be reflective over this imaginary line right here, this diagonal line, the identity function, y equals x. And so this blue function looks like it's going to be 1 minus x squared. So it looks like it's going to be a u that just comes down, right? But it doesn't reflect exactly. This part over here, I don't need. And the reason that is because there's a domain restriction on it. I'm just wanting the right half of this graph. I'm just wanting the part where x is greater than or equal to 0. And the reason that is, remember, I said that my domain and range are going to switch. If you look at the range of this red graph right here, this range is greater than or equal to 0. Okay, the y value, I guess. And so it makes it so that whatever my range was here became my domain. So that's just a little bit of extra, but being able to find the inverse is the main idea on this. Okay. All right, that's all I got for inverses. Be a good time to take a break if you need to. Maybe a drink of water, go do some running, run off some energy, something. All right, let's talk about logarithmic functions. Now, a logarithmic function is going to be the same as my exponential function, except for it's, again, going to just be the inverse of it. So they share a lot of the same properties. So we talked about in the last video that the exponential function is going to look something like this. It's going to be like y equals, I guess, 2 to the x. If I reflect this over this imaginary line that's running through here, what it's going to look like, so instead of going through 0, 1, I'm going to go through 1, 0. Again, just switching my x's and y's. My log function looks like so. So what does that mean for me? Okay, and so this line right here would actually be log base 2 of x. So let's just get a general saying for this, a general definition. Log base a of x is going to equal y, and that's going to be true if and only if a to the y is equal to x. So again, I've done some switching around of my x's and y's, and whenever I'm undoing this exponential, I have to introduce a log into the equation. There are some cancellation equations. For instance, if I'm taking log base a of a to the x, remember, log base a and then a raised to something are going to undo each other, and it's just going to leave you with x. And that's going to be true for any x that you can think of, as long as x is a real number. All right, since the domain of my exponential function up here is all real numbers. We've also got a raised to the log base a of x is going to equal x. And this is only going to be true whenever x is greater than 0, because I can only take log of positive numbers. Okay? If I pull out my calculator right now and I try to take log of -2, it's going to have an error. Because if I'm just taking a regular log of any number, it is not able to come over here on the negative side unless I have a horizontal shift on it. Our 3 basic log laws from Algebra 2, and last year for that matter. The first one stated that if I have log base a of 2 things being multiplied together, I can take log base a of the first one and add it to log base a of the second one, the second element. And this is going to be true. When is this going to be true? This will be true for any x and y that's in the domain. And I'm going to call this the multiplication property. If I change it to division, I think you can kind of figure out what's going to happen here. I'm going to have log base a of x minus log base a of y. And we'll just call this the quotient. I'll call it division. Quotient property of logarithms. And finally, I have log base a of x raised to the r, where this r dumps down in front. Again, all this should be a review for you. I'm just going to call this the power property. And it's not too much of a stretch to kind of see where this comes from. Suppose I have log base a of x squared. Well, log base a of x squared would just be 2 times log base a of x. And remember what log base a of x, or 2 of these mean. It means I'm going to have log base a of x plus log base a of x. So I have 2 log base a of x's. I have log base a of x times x. And so I've kind of worked a circle around between this multiplication property and the power property. They go hand in hand. The reason this power property works is because of the multiplication property. And so the fact that I can rewrite this with an addition, I just have this same argument on my logs on each side. So I'm going to use the log laws to evaluate these. Have log base 2 of 80 minus log base 2 of 5. Well, I'm going to work it in reverse. I'm going to get rid of this minus sign right here. Because remember what this means. This means 2 raised to what power is going to give me 80? I have no idea. 2 raised to what power is going to give me 5? I can sit there and guess in my calculator for a while and try to come up with something relatively close, or I can use my properties to help me out. Properties say that I can get rid of this subtraction right here, and I can write it as a single logarithm if I just stack up my arguments, the 80 over 5. Well, 80 over 5 gives me 16. So now look what I'm asking myself. I'm saying 2 raised to what power gives me 16? Well, I know what that is. It's going to be 4. So I was able to evaluate this without a calculator and get the right answer. Our friend Leonard Euler wanted in on the action. He said, you know what? If you're using my log, if you're using my E, my 2.71828, whatever it is that you're using, if you're using that as your log base, you're going to have to use it a lot in some of the math that you're going to do. I want you to call it the natural log. So it'd been nice if he would have said like NL, but I think he was like French or Italian or something. And so he ended up over there, you have to put the adjective second after the noun. So it's like log natural of x. So if you see the natural log of x, they're just rewriting it what they had with log base e of x. Now all the cancellation equations will still work with this. So if you need to rewrite it, you can. I don't think we'll have to. We went over this in such a detail last year. But part of your homework tonight is going to be just solving for x. And so one of my cancellation equations says that if I exponentiate both sides by e, I end up now taking e raised to the natural log of x. Remember, that's kind of what I wrote earlier. Is if I had this base and the log match right there, it was just going to leave me with x. And of course, if I exponentiate one side, I need to exponentiate the other. And so my x in this case would equal e to the 5th. If you want to tell me what e to the 5th is, that's fine. E to the 5th works for me. It's an exact answer, and I like it. All right, I'm going to turn you loose on this one. You got to get rid of the e, and you got to work that x down. So go back and look and think about what some of your cancellation equations are in order to get that x to come down. So go ahead and hit pause. Again, I left my answer just as an exact answer, 5 minus natural log of 10 over 3. If you need to take that to a decimal, you should have got something about 0.899 or so. I'll accept that answer as well, okay, being able to solve this. All right, let's talk about condensing logarithms. Using my log properties to write my expression right here as a single log. If I want to write this as a single log, first thing that needs to happen is I need to use my power property. My power property is going to bring this 1/2 back up to the exponent. Okay? So if I'm going to write it as a single log, I'm going to need to use my quotient property and or my multiplication property. And in order for that to happen, I don't want to have any coefficients. I guess I'm going to call them coefficients. I don't need to have any multipliers right here in front of my logarithms. So now, I can write this as a single logarithm using my multiplication property. I have a times b to the 1/2. The book would probably have on this natural log of a times the square root of b. That's fine as well. B to the 1/2 is fine. I'm interested in a correct answer in any version that you can get to it without looking at your neighbor's paper. All right, let's talk about the change of base formula. Change of base formula says that we can calculate any log base. If you notice in your calculator, you have a log button and you have a natural log button very readily accessible for you to use. Okay, and so we don't have like a log base 7 button that's ready to go. Like if I take log base 7 of 3. I don't have a log base 7 button right there ready. It's in there probably in your calculator somewhere, especially if you're using one of these new ones, but you might have to go into a menu. It could be a little bit hard to find. And so what they have come up with was that we can use any log base in order to figure out what this would actually equal. Okay? And the whole idea of this is to make it so that you're using the same log base and just setting up a ratio that looks like so. Now, I don't use log base 10 a lot in this class. We are going to use natural log a lot. So you'll see me using this if I'm needing to evaluate a logarithm. Natural log of x over natural log of a. So I had this student one time. I almost debated telling this story. I almost thought I probably shouldn't because this video is already long enough, but it's such a cool story. I had this student one time. His name was Richard Meadows, and this is while I was teaching at Arkansas State University. And every once in a while in class, I would get something we called a non-traditional student in class, which meant that he wasn't the age of your typical college kid. He actually went to school with my father's older sister. Well, anyway, I put this on the board, natural log of x over natural log of a. That was a change of base for me. He raised his hand. He said, "Mr. Lovelady, why?" I was young at the time, young 20-something. I had no idea. I just knew that was the rule, and you just used it. But it bothered me. I was like, why does that work? All right, so I'm going to actually trace this back a little bit and show you why it works. So if I have y equals log base a to the x, remember, that's saying like a raised to what power is going to give me that x. All right. And so if I take the log of both sides, I get natural log of a raised to the y equals natural log of x. I just chose natural log. You can definitely do log. You can do any log base as long as it's the same. And my power rule says that I can drop this y down in front, right off the a little too quick. And once I do that, I can divide both sides by natural log of a. I get y equals natural log of x over the natural log of a, which is exactly where this came from. So a little bit of extra proof there showing where it came from, but that's the idea. So Richard Meadows, if you're watching this, there's the answer to your question. What has it been, 16 years or so? So finally answered it. So let's just try this little trick with this number right here, log base a to 5. Now, if you know what a raised to some power equals 5, if you know what that is, man, go for it, all right? I don't know what that is. I'm going to have to use a calculator on it. But look at where everything goes. I used to say the big number and the small number, but then it's really confusing if the small number is bigger than the big number as far as value. So I'm going to use the correct terminology on this. This just says I can just take the natural log of the argument. Okay, whatever I'm taking the log of right there, that is the argument. And then the small number in subscript at the bottom is going to be the base. So I can just take natural log of 5 and then divide it by natural log of 8. And what that gives me is, I don't know, let's do like 3 decimal places. 0.774. That's what I got on it. If your calculator has a log base 8 button that you can go into a menu and grab, man, use it. That's fine. Oh, it says go to 6 decimal places. Are you guys not going to tell me? So we got a 3 and then a 9 and then a 7 and a 6. So that would be correct to 6 decimal places as the problem states. Now we've worked this one. This was my how much strontium I had, I believe. We came up with this equation on the last video. Well, suppose I'm wanting to work it in reverse. Okay, so this is kind of like we're finding the inverse of it. So this mass right here is going to be my y. I want to turn around and I want to solve it for t. Alright, so solving this for t, I'm going to act like this f of t is not there. And I'm just going to go ahead and divide both sides by 24. make it so the only thing over here is 2 raised to that power. Now that I've done that, I'm trying to get the t by itself. And so I could definitely use a log base 2 to help me out. I'm going to end up using a change of base formula anyway, so I'm just going to go ahead and take the natural log of both sides. Natural log of 2 raised to the negative t over 25. So I can make these logarithms look a little bit better by using my quotient property on this left side. And I can use my power property on the right side to drop this exponent down in front. Now I'm going to do a little side note out here so I don't have to rewrite a whole step. This is the same as negative t times natural log of 2 over 25. So I'm going to clear that fraction by multiplying both sides by the reciprocal right here. Okay, I'm actually going to tag that negative over here, and so it'll be a positive t. So I would have 25 over the natural log of 2, and it's the negative, times natural log of m, natural log of 24. And that in itself would just equal t right there. There's a lot of negatives floating around in there that we could clean up. I could definitely distribute this negative through these parentheses right here and rearrange those and make it look a little better. But this works for me. Okay? And so my inverse of this, what are we talking about? I guess this was the mass or the number of moles left or something, is going to be, this equation would work perfectly fine for me. And so this tells me the time required it was for the mass to decay to m amount of milligrams. So if I'm wondering, hey, when is this thing going to get down to 2 milligrams? I can just plug in 2 in for this m, and it will tell me how long it should take based off its half-life and working this inverse right here. So that's pretty helpful. And this next bell is about to catch me. I paused the video too long a while ago to debate on telling you the Richard Meadows story or not. But let's talk about this natural log function, okay? The natural log function is just going to be the inverse of this e. Remember, e went through 1 and then 2.7. So this function right here is y equals e to the x. So its inverse is going to be y equals natural log of x. So if I reflect these points, again, I'm going to go through 1, 0, and then 2.71. I think that lands me about right here. I get my log function to look like so. At the vertical asymptote here, I'm not going to pass. So what I want to do with that, let's see how well this works. Oh, it didn't work. So what I want to do with that is I want to graph this function. We're going to try to make it work. I don't know if I resize this graph or not. What do you think? Pretty good. We're going to call it. We're going to call that good enough. Okay. So I've got this basic parent function, and now I'm going to move it around and do the transformations that we talked about a couple weeks ago. So I'm going to start inside the function. This minus 2. I believe it's going to move it to the right 2. So now instead of going through these main 2 points right here, I'm going to move those points to the right 2. So that would be right here. And let's see, 1, 2, right here. Now that's also going to move my asymptote to the right 2. So now if I was done, my function would look like this, but I'm not. It wants me to move it down 1 as well. So I'm just going to take these black dots, move them down 1. You can think about moving the asymptote down 1. It doesn't really move, but this blue line right here would be my answer. Inverse trig functions. Inverse trig functions, well, just in general, trig functions are not one-to-one, so they don't have any inverses. And the reason they're not one-to-one, let's just graph sine real quick. Sine sits here and repeats and goes over this period nonstop. Okay? And so what I have to do with this sine function in order to make it so it passes the horizontal line test is I have to trim it down. I didn't draw this to scale on the x-axis, but I have to trim it all the way down to here so it passes, actually got pretty close, the horizontal line test. And I have to make it so its domain is trimmed down all the way to negative pi over 2 to pi over 2. And the way that we wrote inverse trig functions was we would say sine inverse of x. Okay? Or we also said arc sine of x. And so both of them would only use values on my sine function that range from negative pi over 2 to pi over 2. So what that allowed us to do last year was we were able to do inverse trig functions. Okay? Now if you want to think about this, this is equal to y, and I'm wanting to figure out what the y is. And so if I kick the sine off to this side, I was thinking about sine of what function gives me 1/2. Keeping in mind that this answer right here had to be between negative pi over 2 and pi over 2. And so the only angle that I can take sine of that is between negative pi over 2 and pi over 2 and get the answer to be 1/2 would be pi over 6, 30 degrees. And that value came right off our table, our sine, cosine, tangent table that we made last year. Well, what if they give me a composition of trig functions to use? That'll be a little bit harder. Now, this wasn't one of my nice values off of my table. So I've got a little bit of work to do on this one. What I'm going to do is I'm going to go ahead and just create for myself a reference triangle. Okay? Where this is going to be my theta right here. So I'm going to make it so all this parenthesis part is my theta. And what it tells me about this triangle is that the opposite over the hypotenuse side is going to be 1 over 3. Using Pythagorean theorem, that tells me that this side has to be 2 square roots of 2. So, to figure out what tangent of arc sine of 1/3 is going to be, if I just do some substitution here, and I just let my theta equal this whole angle that I've drawn out right here, I just now have to take tangent of this theta. And remember, tangent is going to be my opposite side over my adjacent side. So if I take the opposite over adjacent here, I get 1 over 2 square roots of 2. Go ahead and rationalize that. We should be ready for that. Square root of 2 over 4. What this will allow for are some cancellation equations. For instance, if I take sine inverse of sine x, that should just equal x, as long as my x is between pi over 2 and negative pi over 2. Or if I reverse it, I'm taking sine of sine inverse of x, that should also just give me x. Alright, as long as x is between negative 1 and 1. Because remember, I can only go up and down on my sine function in the range direction from negative 1 to positive 1. Alright, let's talk about cosine. Using the same argument that we used a while ago, remember cosine is going to be this wavy line like so, that goes from left to right. Fails the horizontal line test miserably. And so what we have to do is we have to just start shaving it down from both sides until we're able to finally get it to pass the horizontal line test. Right about there. Again, not drawn to scale, but ideally that would have been from 0 to pi. Making it so anytime I'm wanting to take cosine inverse of something, I have to make sure that my answer is between 0 and pi. Okay? If I'm going to write this correctly, remember cosine inverse of, let's use x right there, is going to equal y if and only if cosine of y is equal to x. Okay. The big thing we have to remember is that this y right here has to be between 0 and pi. It has the same cancellation equations as my sine function does. I've got cosine inverse of cosine x is going to equal x, and this is going to be true for x between 0 and pi. And I'm going to have cosine of cosine inverse of x is also going to equal x, and this is going to be true anytime x is between 0 and 1. One more inverse function, tangent one. Now, I'm not going to draw all my snakes on the plane, but I'm just going to draw this first one right here. Because obviously if I draw more snakes on the plane like tangent is, it's going to fail the horizontal line test. So I just need one snake on a plane right here. Pi over 2 to negative pi over 2. The bell caught me. Good grief. This is going to be a long video. It's going to be okay though. All right. And so, again, we write y equals tangent inverse of x, and that's going to be true as long as tangent y is equal to x. Big kicker on this one, remember, is that this y right here has got to be between pi over 2 and negative pi over 2. Actually, we're not able to touch it because these are vertical isomotopes here. I'm not going to touch that isotope. Okay. So we got one more example I want to go over. And that's going to be cosine of tangent inverse of x. Again, they didn't give me an actual value right here off my table. They gave me an x. It's kind of like when they gave me the 1/3. And the way I'm going to tackle it is I'm going to draw myself a reference triangle. And so I have tangent inverse of x. This is going to be my theta part right here in the middle. So I'm going to end up just doing a substitution where I take cosine of that theta. And this x right here over 1 is going to help me get the opposite and the adjacent sides. Using Pythagorean theorem, I have 1 squared plus x squared is going to equal my hypotenuse squared. So if I take the square root of both sides, my hypotenuse comes out to just be the square root of 1 plus x squared. So cosine is, let's see, caught another hippie. Adjacent over hypotenuse would be the adjacent side, 1, over the hypotenuse, 1 plus x squared. I am passed out of time on this, so here's the practice problems. That would be good to work. Have questions ready on these, and I will catch you guys next time.